This video will continue and actually finish up our discussion of section 1.2 IVPs. I'm going to extend just take another look at the existence of a unique solution, the theorem in the last video. So that at the top is just the theorem. So let's start here. Verify that that is a one parameter family solution to the DE y prime equals 1 plus y squared. Let's go ahead and do that. It was in another video, but let's just go ahead and put that here. So y of tangent of x plus c, right? And then remember we had to work our way up. Y prime was secant squared. And then the chain rule would just produce a 1. Um, and then notice, okay, the left-hand side, right, is 1 plus y squared, which equals 1 plus tangent squared. And then back like the video, I'm not going to show it again, but that's actually a Pythagorean triple. That's actually equal to secant squared plus x plus c, and that's equal to the right-hand side. We're done. Okay, so that's part A, nothing new there. We just wanted to make sure we are convinced that that is a solution. All right, so based on the theorem, okay, so since this is our first derivative and the second derivative with respect to y, right, the partial of that with respect to y, those are continuous everywhere, right? I can pick any y I want. Okay, if I take that function and I take, maybe we should write those down here. F of xy is equal 1 plus y squared. The only reason I wrote it down is for this. The partial of f with respect to y is going to be equal to 2y. Okay. So those I can plug any y's in. So what they're saying is the region R in the theorem can be the XY plane, any numbers you want. Okay, it says use the family of solutions in part A to find an explicit solution of the first order IVP. And it's that exact same problem, but now they gave us y of 0 equals 0. Now I'm going to plug that in to the function. So remember the function was y, right? I'm going to plug that into y. So I get 0 equals tangent of c. All right, so we have to do a little bit of trig here, which is, I guess, everybody's favorite, right? We want to know for what values of c will that work. Okay, so tangent is 0. Remember that sine over cosine. It's going to be when is sine 0. So that's going to be, we get a bunch here. We get a 0, we get pi, 2 pi. Anytime I hit the x-axis, I'm going to get another one. And it actually goes backwards too. So it goes in both directions. Sorry about that. But all those C's can be that. So I can pick any C within there, but the thing that's going to define that for us is here, right? That's going to tell us which one to pick. So I know that C, that 0 is right there. And then I know, okay, now you might be like, okay, then I can just go negative pi to pi. Well, no, everything here was like what makes that 0, right? That's not what is defined. It's just that's what's saying that C will have to be if I want it to go through 0, 0. What we do from here, though, is I have to figure out maybe even the domain. So I'm going to put domain here, dom of tangent of x plus c, right, is going to be, okay, normally, let's go ahead and I'm going to write a domain of tangent, just of that. Okay, that domain is if I, and I'm limiting it, so it's really infinite. It goes on in both ways that way, but negative pi over 2 to pi over 2. I hope you remember that from trig. And it's okay if you don't. But what this is going to do is this C is going to move it, shift it that way. So the domain for this thing is going to be the same thing. I'm going to put a union this time. And it's going to be negative pi over 2 plus C to negative pi to positive pi over 2 plus C. I could have done minus C and it actually would have worked out the same. Okay, but C in this case, right? I have to pick something here, right? And the C that we said that's going to work with those two things, the only one is going to be right there because of that. So if C is 0, then this thing is defined on negative pi over 2 to pi over 2 when C equals 0. Right? So the reason it can't be, they're saying even though x naught is equal to 0, what we're answering here is Why can it not be negative 2 to 2? The reason it can't be negative 2 to 2 is because tangent of x, because it was 0, is not defined. I'm going to go under here, I'm sorry, at x equals pi over 2. And that's not just the only reason. X is in that interval that they tried to say the answer was, right? So they're saying there's a pi over 2 is 3.4 divided by 2, so it's about 1.5, 1.6-ish, right? So it's definitely less than 2. And the negative one, you could pick both of those. They're not defined, and neither one of those x's are in that interval. That's why. All right, so we had to take a look at it and determine what was the domain of that function to determine if the interval that we're looking at can be it. Cool. It says determine the largest interval of I of definition for the solution of the initial value problem. We just discovered that while we were working it out. It's negative pi over 2 to pi over 2. Because tangent is not defined outside of that. It's not continuous at that point. Okay, so this stuff can be difficult. I know when we do domain and when I teach pre-calc and when I teach calc 1, people struggle with the domain stuff. I'm hoping it'll click. It wasn't too bad for me as I went up. I remember sitting in these classes and being really confused, and then the more I thought about it, the more I was like, oh, that's really a pretty simple idea. If you want a challenge, and I racked my brain for a while trying to understand it, and I can like wave my hands at it, meaning I can really try to explain it, but it's really got to squint your eyes to understand what I'm saying. But try to understand this in layman's term. Why is that true? If if this statement right here, if that's true, then why are we guaranteed a solution? So that would be the theory behind it. If you dig that kind of thing, you might be a mathematician. All right, let's go on. I have one more page for this section, and it's still not anything crazy. It's still just finding solutions. I wanted to talk about this for each one. So y of 0. This is just a Calc 1 problem, but I really want to make sure you guys are seeing this too if we have to graph anything. Y of 0 here is going to be a -1, but the derivative is a 0. And that's because this tangent line has a slope of 0. Okay, at this point, let's do this one. Y of 0, I don't know what that is, let's do 2.25, how about that? And then y prime of 0 at that point would be the slope at that point. So I don't know, -1. It's going to be very difficult for us to actually find that. But here's my estimate. So I guess we could say about. We really wouldn't know what it is exactly unless they gave us maybe some more grid marks or something like that. Okay, so we have that. For those two, it's not bad. That's just Calc 1. It's really just understanding this part, I think, is what trips people up, is you just got to understand it's the slope of the tangent line. So just draw a tangent line, and then if you can actually get the slope, get it. If you can't, estimate. Okay, last problem here. Given this, it's a two-parameter family of solutions of the second order. Um, DE, I don't know what's going on there, but DE, and they gave me the DVE, find a solution of the DE that satisfies, and they gave us those two. So we're going to use those two conditions. This is called a boundary value problem. So this is a BVP, boundary value problem. And the reason it's called a boundary value problem is right here. They gave me y of 0, 0, then they gave me y of prime of 0, or sorry, y of pi is 0. My brain was ahead of myself. No primes, right? It's just two values. It's two boundaries of my function. And then I'm going to have the function I want the function that hits both of those 2 points, the boundaries, but goes through. All right, so they gave us that solution, thankfully. We do not have to solve it, but here's my y. Right, small, because we're going to have to fill in quite a bit here. All right, sine of 2x. Let's go ahead and do each derivative. Okay, I'm going to get a -2c1 sine 2x. They're just chain rules. So if you're struggling with the chain rule, please go fix that. It's not going to just go away. And then double derivative, I get -4 c1 cosine 2x. and then I get minus 4c2 sine 2x. All right, I have all that, and I like to start left-hand side and just try to work my way to the right-hand side, which in this case is just a 0, so that kind of works out for us. All right, I'm going to be a little lazy here. Left-hand side, let's write it down, y double prime plus, and then this is a typo. It's just a y. I wonder if that's a y prime. We'll find out. Let's see if it works or not. It might be a typo where it should be a y prime. So we'll do, I was thinking that, but let's do a 4. Let's just see if that works out. Um, let's think about this real quick. If I take this and I add 4, am I going to get 0? No, definitely not. So right here, I want you guys to take it. Y, if yours isn't fixed already, 4, Y prime, I'll use these videos for a bit of time. So yours might be fixed at this point. Okay, so I got a Y prime there. That doesn't fix any of the work that we've already done. We just have to put a Y prime here. Cool. Now it's probably going to work out. All right, so I'm going to take my second derivative. I'm just going to copy and paste. Sorry, you'll have to probably write it out unless you're using tablet. Plus 4 times, and I'm going to do the same thing with my first derivative. Okay, right. And actually, I'm starting to think that that is a, because that's not going to work either. No, I think, okay, so I think the problem was no prime. So write it like that. There we go. Okay, so that's going to work out. And I just realized they never told us to verify. But here we are, and we're practically done verifying, so we're going to continue. All right, so this is equal to, you can see that everything here is going to cancel out. If you're on a test, I'd recommend you just do one more just in case you mess up. I can squeeze out as much partial as possible. But yeah, okay, there we go. And then now they want us to find a solution with those, and we're going to come up, this is going to give us a system. So y of 0 equals 0, y of pi equals 0, and this, if I plug them both in, okay, I get 0 equals, and I just plug them into the y. Okay, cosine of 0 is a 1, so I get c1 plus c2 times 0. And then the other one, I'm going to get a 0. And then if I type in, if I put a pi there, I'm going to get a 2 pi. Cosine of 2 pi is still, it's just a 1. And I'm going to get also c2 times 0 there. So, kind of interesting. Let's see, actually, let me double check that. 2 pi, yeah, definitely. So that's what we get here. This is actually going to provide us with C1 being 0. And then by what we have here, I think C2 really could be anything we wanted. Let's check that out. So C2 equals 0. Let's try if that solution would work. Remember our solution, our diffeq is y prime plus 4y equals 0. We had to change it twice. And then remember our y is now going to be, if they're both 0, y equals 0. That one worked out, but we call this the trivial solution. We don't really want to use these because it's like a super easy answer when there could possibly be an easier, more complicated answer. And later on, we're gonna have diffie where this is an answer, and then we actually have something else as an answer as well. So let's try something else. Remember, C2 is the one I can change. I don't think we can change C1. So let's try, what if it was y equals, and then I only keep sine of 2x. See if that works out. So y double prime. Okay, so y prime, maybe we should start there. Y prime is going to be 2 cosine x, 2x. And then y double prime is going to be negative 4 sine 2x, right? If I take that and I add it to the original, when that one's times 4, right? That's what this is saying. It works out. So that's the solution as well. All right. Now, here's the deal, though. We have to make sure that it fits and it hits our boundary problems. So make sure if you plug in 0, it hits each one. So if I plug in 0 or I plug in pi, I'm going to get 0. So this is the better answer. You could choose almost anything you want. It says the condition specified, find a solution, gives us those. Because of the way this worked out, C being where it can, C2 where it could be anything. Um, it just kind of is great there. We get just a bunch of answers. That doesn't typically work out all the time where you get a bunch of answers. Sometimes when you work it out, you get down. Remember, you just get C1 is this, C2 is this, you get one solution. But in this case, this is the reason I picked this one, is that it is very strange that the C2 just kind of went away down here. When that happens, like I said, C1 had a designated value. Um, C2, we're going to have to find something else out because those are zero regardless of what C2. It will work out regardless. Okay, so there's that solution. It's right here. All right, so that's the conclusion of that section. Some of this stuff gets kind of strange with the theory. My recommendation is try to, if you're confused about what theory is saying, seek out an example that isn't theory, that's applying it, or try to apply the theory to an actual problem, and maybe the theory will get a little better. Okay, good luck.